An A36 steel column has a length of 4 meters and is pinned at both ends. If the cross-sectional area has the dimensions shown, determine the critical load. Okay, so we're trying to find the critical load. And remember, the critical load, that is where our column will buckle, and that's given by the Euler equation, pi squared EI over L squared. Now, that's important. It's pinned at both ends, so it falls into that ideal column that we dealt with. And one thing to note, this is the cross-section. This is not the... So this thing is actually a column that's 4 meters tall. This is just, if I cut away and took a look at it right here, this is what... So it's a plus-shaped column. I bring that up because I once gave this problem on exam, and somebody thought that this was a column, and all kinds of confusion ensued. So this is the cross-section of it. Now, what we're looking at, the cross-section, that's going to be important because we need to calculate out the moment of inertia. Now, in this case, you'll see it's symmetrical. So the moment of inertia in the x direction and the y direction are completely the same. So that means it has an equal chance, if it's going to buckle, an equal chance of buckling in either direction. Of course, I'm making the motion with my hand to show which way it's buckling that you can't see. So let's take a look at this guy. And so one of the first things that we have to do is we have to do the area, because we're going to need the area. So what do? Well, we're just going to break it up into a couple of different parts. And so if I start with this middle part here, it's going to be 10 millimeters. I'm just going to convert that over into meters. And then that's 10 millimeters wide. It's 60 millimeters high, 0.06 meters. And then I have this guy across the middle here. We're going to add to that. It's 10 millimeters wide times 25 millimeters to here. So 0.025 millimeters. And so that gives me the area here. And then we'll multiply by 2 to get the area over there. So that'll give us the entire area of the column. And so if I multiply that out in my calculator, I get 1.10 times 10 to the negative 3 meters squared. Next thing to do is calculate out our moment of inertia. So in this case, Ix is the same as Iy. So as we look at this, we're going to typically end up having to deal with the parallel axis theorem with columns, because a lot of times they're going to be I-beams and whatnot. The positive thing with this is typically as we're looking at columns, any of the complex shapes, we're going to be looking at rectangles. Now, if I have a circular shape, I'm usually not going to be using the parallel axis theorem because it's just going to be one circle. It might be a hollow circle, so we take the moment of inertia of the outside, subtract the inside to find out what the ring is. But it's very unlikely that we're going to have columns that'll be a circle with a rectangle coming down. I'm not saying that can't happen, but it's pretty unlikely. And so, which is nice because when we're dealing with rectangles, they're all just base height cubed over 12. Makes it pretty simple. Now, also with these, it's the parallel axis theorem. So what is the parallel axis theorem? Remember, that's going to be the sum of all the moment of inertia about the centroid plus AD squared. If we can set our things up that when we break up the bigger shape into the littler shapes and say that, okay, well, my d squared is going to be 0, that will make it easier for us to solve. So, case in point, let's take a look at this guy. So if I'm looking for the moment of inertia about the x-axis, so those d squares are going to be the centroid from the composite shape to each little individual piece. So in this case, the centroid of this composite, since it's completely symmetrical about all those axes, it's going to be right there along this x-axis. Now, since we're looking d squared is going to be talking about what's the deviation from the x-axis. So in this case, if I broke this up into pieces like this, and I've got my centers of my 3 pieces are there, well, my d dimension is going to be right there, because I'm deviating from the x-axis. But if I'm smart about things, and let's say that I break it up in this way, So my center would be here. My center would be here. There is no deviation in the x-axis. They all lie on the x-axis. So there is going to be no deviation. The composite centroid is exactly in the same place the centroid of this middle piece is, and on the same x level as these other two pieces. What does that mean? Well, that means d is 0. And in this case, since it's symmetrical, ix and iy are the same. And I mean, you could do the same thing and go, okay, well, let's do the moment of inertia about the y-axis. Well, my centroid's in the middle there, and so now if I break it here and here, the centroids of those individual pieces are going to lay along that y-axis. So once again, there's no x deviation, so there is no d. D is going to be 0 because they lie on the same thing. There's no multiplier effect for it to be farther out from the centroid of everything than the other ones. And that's important because it can make things like this actually pretty quick to calculate, because you sit there and go, okay, well, I'm going to break it up like that. There's my centroids. I have no d squared for any of that. So I've got base, which would be 10 millimeters, times my height, in this case it would be 60, cubed over 12. There's no ad squared because d is 0. And then over here I've got base, 25 millimeters, just 0.25 meters. I've got the height, 25 millimeters. I'm going to cube that, divide that by 12, and we'll multiply that whole thing by 2 to get my two sides. And so that's just, it's a way of making things a little bit simpler when I'm calculating out what my moments of inertia are. So always try to take a look at things and make it easier on yourself. I mean, when you can do stuff like that, or if you have a rectangular box with a hole in the middle of it, just moment of inertia, the entire thing minus the smaller thing, make your life easier. Don't make your life more difficult. And so there we go. So, oh, we actually need to calculate that out. So if I go and I plug that into my calculator, we should get 184,167 times 10 to the negative 6 meters to the fourth. And so now I have all the information to calculate out my critical load. So my critical load is going to be pi squared EI over L squared. So pi is easy, everybody knows pi. E is given to us in the problem, 200 gigapascals, so 200 e to the 9th Newton meters squared, which is why I converted everything over to meters squared. 184, I don't need to carry out all the rest of that, times 10 to the negative 6 meters to the fourth. Divide that by L squared. What was it? L? Well, L is the length of that guy, so 4 meters squared. Probably wondering why is the area not in here. Remember, we're going to need the area for calculating out the critical stress, because we need to make sure that that falls below the yield stress. Okay, and so this is what we have. We just plug it into our calculator, and we're going to get 22,720.65 newtons, which is 22.7 kilonewtons. So this is possibly our critical load. And the reason I say it's possible, because remember, the Euler formula is only valid for one situation, when our critical load is less than our yield. So if I go and look up what my yield strength of A36 steel is in my engineering manual, my yield strength is 250 megapascal. So let's calculate out critical stress. 22.7 kilonewtons. I'm going to divide that by our 1.10 times 10 to the negative 3 meters squared, and that will give us 20.66 megapascals, which is less than 250 megapascal. What does that tell me? Well, that tells me that this is going to buckle before the material fails. Which direction is it going to buckle? It's got an equal chance of buckling in the x and the y, and the reason that is because the moment of inertia in the x and the moment of inertia y are the same. If I calculated out the critical load, and let's say that the moment of inertia of y was half that as x, I'd have two different critical loads. I would have the x, which would be 22.7, and then I'd have the y, which would be 11.35 kilonewtons, and so I would be able to say that, okay, this fails from buckling. It's going to buckle in the Y direction because it has the least critical load. Now, if I went and figured this all out, and this was my critical load, and when I calculated out the critical stress, it was 260 megapascals, which is greater than the yield stress of the material, the column doesn't buckle because it never gets a chance to buckle because the material is going to fail. It's going to shear apart before it gets a chance to buckle. This is a very, very important distinction between the three. And I'm going to say it again. This is the kind of thing that I'm going to ask you on an exam. Is it fail because of material, X or Y? And so that's an important thing to know.